As was already mentioned, our next speaker is also speaking about the Planck project. It's also our last speaker, our last presentation for today on stage, Bob. His name is Oliver Holschke, and he is Architect Future Networks and AI Program at the Telecom Innovation Laboratories, or short T-Labs. He investigates quantum technologies there, and his focus topics are quantum communication and security and quantum annealing for combinatorial optimization. Welcome, Oliver, and I'm looking forward to your talk now.
Yeah, thank you, Roman. Hello, everybody. My name is Oliver, and I work for T-Labs, which is part of the Deutsche Telekom group, and we do R&D there. And the focus topics, Roman mentioned them just now, is quantum technologies, and within several technologies, quantum computing is also of interest to Deutsche Telekom. And today I would like to show you how we are involved in the Planck project, which is funded also by the Ministry of Economics and Technology. And you just heard a presentation by Tim and David about that project. And I will give you an overview of the use cases that we are bringing into the project and that we are investigating with regards to quantum computing. So just a quick intro slide on the T-Labs. So that is what we do. I work in Berlin, and we explore and develop technology options for more powerful communications, security, and computing. When it comes to quantum technologies, actually for all these three, this is of relevance. But when it comes to the project Planck, the emphasis is on the computational capabilities that we are evaluating there. So what can you expect over the next 20 minutes? So I would like to tell you about our initial approach regarding the Planck project, how we framed the problems there, and what our objectives are in the project. Then I'm giving you an overview of use cases that we're addressing, and give you a little bit of rationale there, why DT is taking them, is looking at them. And then the third point, then a general methodology. So how we usually approach these use case transpositions, you could say, yeah, to do that with quantum computing. It's there's lots of steps are then repeating in themselves. And then I just dive deeper a little bit on one of the use cases, just to give you a little bit an impression of then how that looks like when a QUBO is developed, yeah, and then how different models are looked at and what we learn by doing that, and in the end then the learnings that we gather through this Planck project. Okay, so our approach of the T-Labs in Planck, so we want to explore this application potential, definitely, of quantum computing with regard to industrial use cases. So we have to select some applications that are somewhat meaningful to customers of ICT. And then we want to get started simple, yeah, and get our hands dirty, basically, and use quantum computing and get some first results. Yeah, could be start with simple problems and then take it from there. Yeah, expand the complexity, and by that learn about it. Yeah, and learn about all the parts that are necessary to go from end to end. Yeah, then if it's possible, then of course we want to do benchmarking. Yeah, is it really better than what we currently do? Of course, then we would need to have a comparable problem size, yeah, a comparable problem complexity. Sometimes that is the case. Sometimes it's a starter, yeah, with a smaller problem, but then we will get there. Yeah, it's also about learning alternative problem framing, just looking at a problem a bit differently in a quantum way, you could say, decomposing a problem. So these just looking at the problem a bit differently. That's also a good opportunity when approaching this with quantum computing. And of course, we want to engage with the domain expert colleagues in the Planck consortium, which is excellent because this fertilizes then the discussion on problems we have, equivalent problems in other domains that will be fruitful then to what we do. So this is a really great people network, of course. So the use cases that we have been addressing so far during the first 16 months, you can see them here. It's 5 basically. The last one is a bit of a box, the inspiration for further use cases. This is, of course, what we will do then in Planck in the coming months, but also it's an inspiration for if we look internally, right, into internal domains of the BT group, that's of course very fruitful. So what do we have here? We have a job shop scheduling. Why could that be interesting? DT has also an ICT integrating business with T-Systems, with customers in the industry, quite huge organizations, and also manufacturing. So combining that with computing services is always interesting and a business opportunity. And there has been some experience before there in that department. The next one, field service optimization. That's something really like easy to relate to, because the Deutsche Telekom service is out there and fixing problems, and there's a lot of them, and how do they do their tours, and is that actually done in an optimal way? And then there's road traffic optimization. There's a connection to smart cities, and then there's 2 more that are internally. The IP traffic engineering and the anomaly detection. Here's some more points for the background on these use cases. So there's like 7,000 colleagues in the field service, for example, just to give you like a number, how many are out there and how many tours that are and how many to how many jobs that relates to. The road traffic optimization, that's a problem then for switching traffic lights to control traffic congestion. So there is also with T-Systems some business opportunities targeted towards a smart city. It's fair to say that it's maybe not the first thing that comes to mind, when thinking of Deutsche Telekom, but there is these overlaps of domains that makes it interesting also to attend to these problems. And then number 4 and 5 that are really core business, IP traffic engineering. You have problems there called like multi-commodity flow routing, more a theoretical problem, because in practice we are dealing with shortest path routing or segment routing. This is then really a daily business and also evolving, and for that benchmarkings can be done because there it's quite easy to look at the way things are done right now, really in the domain, right, by the colleagues and the subject matter experts. And a newer case here, the number 5, the anomaly detection in network flow data, for example. It can be in other data streams. There we are going towards learning, because the first 4 are more on combinatorial optimization. But here with this one, we are starting to get into machine learning cases and doing those on with quantum computing. To get labeled data sets is not as easy as it maybe would seem, even if you're in the organization. But it's a very layered and complex system in the status quo with just different systems involved, and to really get to labels like this anomaly means this bug or error is actually, it's not so straightforward, as you have to really dive deep into your own organization. And being in an R&D unit is also kind of being at the periphery sometimes, but it's definitely our objective to also to get to that data to do good benchmarking. Okay, then that was an overview of the use cases we have addressed, and now it's a very short wrap up about how these are addressed methodologically. So what people in our team usually do, right? It starts with a problem mapping. So this maybe even interesting if you're targeting something similar in your organization. So for us, it means to really get in touch with the domain experts. And this already sparks very interesting discussions. It also helps to, or it can engage the domain as well, to get them also excited about this technology option, to do things on a quantum computer. And this can be already quite constructive. This first problem mapping approach, if you have the domain on board. Then, of course, some translation work has to be done to get these things into what are the variables, what are the objectives, what are the constraints, and develop them. And then ultimately it turns into this Hamilton operator. So we get it into some energy function that we then want to minimize. So that is always a step involving lots of loops, to get to the right one there. And then, of course, it's not like in that sequence, the step number 4, because it happens in parallel in a way, leveraging the state of the art, what is out there, because lots of things are being published, also presenting QOs for maybe the exact problem you have or something very similar. So this can be very inspirational, and this should be tapped. It's a great resource, and lots of things are on archive nowadays. It's kind of easy to get. You just have to invest in a little bit of search there. Of course, the Planck partners, the consortium, a great resource, to discuss maybe similar problems, that are maybe compatible. It's always very fruitful, to get insights from maybe adjacent domains. And then the internal domains, I already mentioned them. Usually, or ideally, you get them from the very beginning. Then there's a step of programming the hardware, actually, the quantum computer. So what we have done in the use cases I showed, that's usually so Fujitsu with the digital annealer, then also a D-Wave. That's what we have done, and we're now in the process of doing a use case also on the IBM-Q. So we're just in the prep works for that. The Fraunhofer network is basically handling the access to that machine in Ehningen, and right now the contractual work is, I think, being reviewed, and once that is through, we'll get one of our colleagues then to execute something on the IBM-Q. So that would be then in a way the third hardware, we would be exploring. In the end, of course, an execution, a result, and then a comparative evaluation, some kind of benchmarking. Does it really move the needle? If we can compare it, that's of course then the most interesting step then for the domain, the internal domain. Not really for us as R&D, because we want to learn these things step by step. But then with regard to the impact, of course, this comparative evaluation is crucial eventually. All right, so this was an overview of the methodology. What we go through these steps. And now it's just a little deep dive. Yeah, I won't go into formulas. It's just to give an impression. I took the field service optimization problem here, and it was actually done by a colleague that was with us, Theo Körner. He's maybe in this here in the audience, who did that and approached it with various models involving, let's say, the most obvious variables and constraints. These job visits, yeah, at customer sites. Then there's a central depot, yeah, the people have to return to, and then formulating the energy function for that. Also finding out then there's strengths and weaknesses with the different problems. Sometimes there's very prohibitive constraints that are being introduced that really eat up a lot of resources that also came up. And in the end, it's actually also further operational constraints that that remain open. So this is what that was kind of an intermediate step here with these operational constraints that really needed to be considered from practice, but they weren't addressed at the time, but are being addressed now because we already went further with this. So Ming, another colleague, who basically took the problem on and went deeper and tried to map more variables into it. So just to illustrate it a bit, so the skill requirements of the service, of the field service, is of course also a constraint. Not everyone knows everything for every job, but there has to be some matching and clustering of these things. Then there can be like instant priorities. Yeah, different jobs have different priorities. Something could be very urgent. Yeah, that changes things, of course, on the fly maybe. Then there could be access limitations to the actual house. Yeah, so for example, opening times of some company, or let's say parking availability. Yeah, you name it. These are all very practical further constraints that must be considered to get to the real optimization problem. And then the last one that was really something that in the first phase was not considered, but now Ming has introduced it into the QBO, is the actual work duration. So the duration of time is actually, of course, naturally, it's a resource. So getting from A to B is not the same as getting from A to C, and how much time you would expect to spend on a job, yeah, is also, of course, what has to be considered. And this is what's being done at the moment. So I already see Roman, and I come to my last slide. So Planck is a great project, yeah. So we thank the Ministry for Economics and Technology. It brings together people working on similar challenges. The quantum community, computing community in Germany is, I think, everybody's talking to everyone. I think it's very dense. It's a great network. The discussions, they sharpen the focus, yeah, also for our challenges ahead of us. We have the opportunity to get to different quantum computing hardware and platforms. And overall, it's a great catalyst, yeah, to get to deeper quantum computing understanding for an industry partner, yeah, for rather a user of this. It just accelerates things a lot. So thank you very much for your attention. And with this, I would I stop, and it's the last slot, right? And we want to end the day maybe.
Thank you very much, Oliver. I think that was a great conclusion to this block and also to our stage today, showing more in detail now on the Planck project, especially how you make best use of the possibilities there, what you've already achieved, and where we are going with that, and how you can use all the different, make use of this partner network and can use the different hardwares as well. So thank you very much for this talk. Like the other speakers, Oliver will be available in the speaker section, in the Meet the Speaker section afterwards now. So if you are interested in engaging with him and further discussions, have further questions, please feel free to meet him there. Thank you once again, Oliver. And yeah, as he has already mentioned, we are at the end of today's program on stage Bob. On stage Alice, it's actually still going on. We are having our fireside chat on stage Alice now for another 40 minutes approximately until we are through with today's program of the Quantum Summit. But we will be back tomorrow. We will be back tomorrow on both stages, of course. On stage Alice, we will start at 9 o'clock tomorrow, and on stage Bob, that means here, we will start at 9:10. We have a lot of further very interesting talks tomorrow. While today we concentrated on quantum computing almost entirely in this section on stage Bob, tomorrow we will have different focuses. We will first have a focus on quantum communication and cryptography tomorrow. Afterwards we will focus on quantum sensing. And towards the end we will have another short section on quantum computing and simulation. With that, I want to thank you. I want to thank all of you for being with us today. I want to thank you for following our presentations, our Quantum Summit, for engaging with us in the chat and with the speakers. And I hope we see you again tomorrow. Thank you very much. See you tomorrow, and goodbye.